a major European financial institution. 1999, their engineering team makes a confident call. Everything on CORBA, the Common Object Request Broker Architecture, as the backbone of their next-generation trading platform. Over the next 4 years, $40 million in integration work, middleware licensing, and consulting fees. Then REST arrives. Then SOAP gets abandoned. Then their entire distributed object layer becomes a liability no new hire can maintain. By 2005, they are rebuilding from zero. The tragedy is not that CORBA was technically inferior. The tragedy is that the engineers who chose it were not wrong by the standards of their moment. They simply bet on the wrong abstraction, the wrong layer. And the market punished them for a decade. Right now, in 2024 and 2025, every engineering team building multi-agent AI systems is standing at exactly the same crossroads: MCP or A2A, Anthropic or Google, protocol or agent protocol. The graveyard of failed standards is full of confident architects. By the end of this lecture, you will know which bet carries existential risk, and why the framing of that question itself may be the most dangerous trap of all. Let us place this on a concrete timeline so you can feel the velocity of the collision. November 2024, Anthropic releases the Model Context Protocol, MCP, as an open standard for connecting AI models to external tools, data sources, and APIs. Adoption is immediate and aggressive. Within weeks, major IDA vendors, API platforms, and enterprise tooling teams are shipping MCP integrations. The community reaction is overwhelmingly positive. Then, April 2025, Google DeepMind drops the agentic protocol, A2A, positioning it explicitly as the missing standard for multi-agent orchestration. The Hacker News thread hits the front page within hours. The top comment reads, "So which one do I actually use?" That single question, asked by thousands of engineers simultaneously, is the clearest signal that a standards war has officially begun. Notice the pattern. MCP was designed to solve the AI-to-tool connectivity problem. A2A was designed to solve the AI-to-AI coordination problem. These sound like different problems, but in a real multi-agent system, they collide at every architectural boundary. And that collision is exactly what this lecture is built to help you navigate. Because the next section will show you a structural map, how you see both protocols entirely. Before we go deeper into the technical anatomy of each protocol, let me be explicit about what this lecture will arm you to do. Because abstract knowledge without decision capability is exactly how engineers end up choosing the next CORBA. After completing this lecture, you will be able to do 5 things with precision. First, classify any agent system requirement, MCP domain, A2A domain, or hybrid, without ambiguity. Second, evaluate a proposed architecture and identify where protocol layer conflicts will emerge before they become production incidents. Third, a justified recommendation for your team or stakeholder, one that survives adversarial questioning from both MCP advocates and A2A proponents. Fourth, recognize the specific organizational signals, team structure, vendor dependencies, compliance requirements that should shift your protocol weighting. Fifth, design a coexistence strategy where MCP and A2A operate in the same stack without creating integration debt. These are not theoretical exercises. Each capability maps directly to a real decision gate that senior engineers and AI platform architects will face in the next 12 months. The question is not whether you will face this decision, it is whether you will face it prepared. Now here is the structural insight that everything else in this lecture rests on, and it is the one that most protocol comparison articles completely miss. The question MCP versus A2A, which one wins, is structurally equivalent to asking TCP versus HTTP, which one wins. It is the wrong question. Because TCP do not compete. They operate at different layers of the OSI model, and both are necessary. TCP handles reliable transport between nodes. HTTP handles application-level semantics on top of that transport. Remove either one and the system breaks. MCP and A2A have an analogous relationship in the multi-agent stack. MCP operates at what we might call the tool interface layer. It defines how an AI model connects to external capabilities, APIs, databases, file systems, computation engines. A2A operates at the agent coordination layer. It defines how autonomous AI agents discover each other, delegate tasks, and exchange structured results. These are not competing answers to the same question. They are answers to 2 different questions that must both be answered in any serious multi-agent architecture. The engineers who understand this separation will build systems that scale. The engineers who treat this as a binary choice will rebuild their systems in 3 years, just like our friends at that European bank in 1999. In the next chapter, we will look at the historical pattern of every major protocol war and use it to predict exactly how this one resolves. Every decade, the distributed systems world fights the same war, and the loser is always the protocol that forgot why simplicity matters. In 1991, CORBA promised a universal OCT-bus. It was technically brilliant, backed by the OMG consortium, and adopted by every major enterprise. By 2000, it was collapsing under its own specification weight, over 800 pages of IDL contracts. Then SOAP arrived, structured, XML-based, and WS-laden complexity that made CORBA look lightweight by comparison. REST didn't win because it was technically superior. It won because a developer could understand the entire model in 30 minutes. And GraphQL. It didn't replace REST. It carved out a precise niche where REST's overfetching problem was too painful to ignore. The pattern is always the same. Complexity accumulates, a simpler challenger emerges, and the ecosystem votes with adoption velocity. The question you need to be asking right now: which side of this pattern are MCP and A2A on? If you want a single historical analogy that maps perfectly onto the current agent protocol war, it is not CORBA versus REST. It is SOA versus ESB versus microservices. Because this is the only protocol war that was also an architectural philosophy war, and that is exactly what MCP versus A2A represents. SOA in the early 2000s was correct in principle. Separate concerns, define service contracts, enable reuse. But then the ESB arrived, the enterprise service bus, and turned every integration point into a centralized, vendor-controlled choke point. IBM WebSphere, TKO, Oracle SOA Suite. These were the ESBs that promised to manage all complexity centrally, and they did manage it, right up until the complexity of managing the manager exceeded the original problem. Microservices didn't solve this by adding more features. They solved it by removing the central authority entirely and pushing contracts to the edges. The lesson for today: any protocol that requires a central broker to coordinate agent-to-agent communication carries ESB DNA, and ESB DNA has a known terminal diagnosis. Here is what makes this analogy incomplete, and that gap is exactly where the real insight lies. Across 30 years of protocol wars, 3 structural laws predict survival with near-perfect accuracy, and they have nothing to do with technical superiority. Law 1. Adopt simplicity. The winning protocol can be understood and implemented by a new practitioner in under 1 hour. REST passed. CORBA failed. Law 2. Ecosystem network effects. The protocol that controls the largest adjacent tooling ecosystem creates switching costs that no technical argument can overcome. HTTP won because browsers existed. Law 3. Scope precision. Protocols that try to solve everything solve nothing adoptably. GraphQL survived by refusing to replace REST entirely. It carved a precise, non-overlapping niche. Now apply these 3 laws to MCP and A2A. MCP scores high on adoption simplicity. Any developer who understands JSON RPC can implement it in an afternoon. A2A scores high on scope precision. It explicitly targets agent-to-agent coordination that MCP does not claim to address. The question is whether either protocol achieves the ecosystem network effects needed to cross the adoption threshold. That question requires us to understand exactly what each protocol is, which is precisely what the next section will reveal. Here is the state of the multi-agent ecosystem in 2024, and it should make any senior architect uncomfortable. We have LangChain implementing its own tool calling abstraction. AutoGNN has a completely separate agent communication model. CrewAI defines its own task delegation protocol. LlamaIndex uses yet another integration pattern. Every major framework has, in the absence of a dominant standard, invented its own coordination language, and none of them are interoperable by default. This is not a new phenomenon. This is the exact fragmentation pattern that preceded every major protocol consolidation in history. Before REST unified web APIs, every major platform, Amazon, eBay, Salesforce, had incompatible web service dialects. The consolidation happened not because a standards body mandated it, but because one approach lowered the integration cost so dramatically that fragmentation became economically irrational. The dangerous question for today's agent architects: are you building on a framework dialect that will be deprecated when the consolidation happens? Because history says the consolidation is not a possibility, it is a certainty. The only variable is timing, and timing determines whether your architecture survives the transition. The single most clarifying framework for understanding MCP versus A2A is not a new one. It is the OSI 7-layer model, invented in 1984, and still the most durable conceptual tool in distributed systems architecture. Here is the reinterpretation that changes everything. MCP, the Model Context Protocol, operates at what we would call the tool interface layer. It defines how an AI model connects to an external capability: a database query, a file system read, a web search API call. This is analogous to OSI Layer 6 and Layer 7. The presentation and application layer, where data format and application semantics are negotiated. A2A, the agent-to-agent protocol, operates at the agent coordination layer. It defines how one autonomous agent's agent discovers, delegates to, and receives results from another autonomous agent. This maps to OSI Layer 4 and Layer 5, the transport and session layer where connection management and logical communication channels are established. The critical insight that resolves the MCP versus A2A framing entirely is that OSI layers do not compete. Does not replace Layer 7. TCP does not obsolete HTTP, and if this analogy holds, MCP and A2A are not competitors. They are complementary strata in an agent communication stack that does not yet have a name. That is what the rest of this lecture will build, layer by layer. Starting with MCP in the next chapter. Let's open the hood on MCP, the Model Context Protocol released by Anthropic in late 2024. At its core, MCP is a three-tier architecture built around three distinct roles: the host, the client, and the server. The host is your LLM application, code desktop, cursor IDE, or any orchestration layer that holds the conversation context and issues requests. The client is the protocol handler embedded inside the host. It speaks MCP natively, manages connection lifecycles, and enforces capability negotiation. The server is where tools and resources actually live: a database connector, a file system interface, a web search API. The genius of this separation is borrowed directly from classical software architecture. You isolate intent from transport from execution. This is the same principle behind the OSI layered model. Each layer has one job and one contract. Anthropic designed MCP so that any LLM host can connect to any MCP server without custom glue code. That is the value proposition in one sentence. But here is the question you should already be asking: what happens when the host itself needs to be coordinated by another agent? We will get there very soon. Now let's go one level deeper, the transport layer. MCP supports two primary transport mechanisms. First, STIO, standard input-out, used when the MCP server runs as a local child process on the same machine as the host. The host spawns the server process and communicates over STIN and STOUT pipes. This is fast, simple, and requires zero network configuration. Second, HTTP with server-sent events, or SSE, used when the MCP server is remote. The client sends requests over HTTP post, and the server streams responses back over an SSE channel. Both transports share the same message format, JSON RPC 2.0. Every MCP message is a JSON object with a method, params, and an ID for correlation. The communication model is fundamentally synchronous at the request level. The client issues a request, the server processes it, and returns a result. This is a deliberate design choice. MCP was conceived for the AI-to-tool interaction pattern. The LLM needs a tool result before it can continue reasoning. Streaming via SSE handles latency, but the logical flow remains request-response. Think of it as SOAP's synchronous contract with REST's transport simplicity. The synchronous model is elegant for single-agent workflows, but as we will see shortly, it becomes a structural bottleneck when you need agents talking to agents asynchronously. MCP exposes exactly four primitives, and this taxonomy is worth memorizing because it defines the entire capability surface that any MCP server can offer. First, tools, executable functions the LLM can invoke, like running a SQL query or calling an API. These are the verbs of MCP. Second, resources, structured data objects the LLM read, like files, database records, or documentation. These are the nouns. Third, reusable prompt templates that a server can register, and the host can inject into the conversation context. This is underutilized but powerful for domain-specific workflows. Fourth, sampling, a reverse channel where it can request the LLM to perform an inference call on its behalf. This inversion of control is architecturally fascinating. The tool is asking the model to think. Together, these four primitives cover the vast majority of LLM-to-tool integration patterns. What they do not cover is inter-agent coordination, and that absence is not an oversight. It is a scope decision. The question is whether that scope decision ages, well as multi-agent systems become the norm. 6 months after its open-source release, MCP's ecosystem growth has been genuinely remarkable, and understanding who is adopting it tells you everything about its trajectory. At the center is Anthropic's own Claude Desktop, which ships with native MCP client support, giving every Claude user immediate access to the protocol. Cursor IDE followed rapidly, embedding MCP to let developers connect their coding environment to arbitrary tool servers, turning DE into a composable AI workbench. On the server side, the community has produced hundreds of open-source MCP servers. GitHub connectors, Postgres adapters, Slack integrations, Notion bridges, and more. Major platforms including Cloudflare, Vercel, and Replit have published official MCP server implementations. From an adoption velocity standpoint, this mirrors early NPM growth patterns, a permissive open standard with a low integration barrier creating a positive flywheel. The developer segments driving this are predictable. Application builders who want tool connectivity without writing bespoke integration code, and platform vendors who want to become accessible to any MCP-compatible LLM. But notice what is absent from this ecosystem map. There is no native multi-agent coordination layer. Every node connects to an LLM. No node connects to another agent. That structural gap is exactly where our next scene begins. Now for the honest reckoning. MCP has 4 structural limitations that any enterprise architect must understand before committing to it at scale. First and most critical, MCP has no native agent-to-agent communication. The protocol assumes exactly one LLM host and one or more tool servers. There is no primitive for an agent to discover, address, or delete to another agent. If you try to build a multi-agent system purely on MCP, you end up hand-rolling coordination logic that the protocol was never designed to carry. Second, state management is minimal. MCP connections are stateless at the protocol level. Persistent session state, conversation memory across tool calls, and long-running task tracking all fall outside MCP's scope. You must implement these yourself in the host layer. Third, the security model was designed for single-model, trusted operator contexts. MCP servers receive calls from one authenticated host. The moment you introduce multiple agents with different trust levels, you are beyond what the protocol's security primitives can natively enforce. Fourth, the scalability ceiling. The synchronous request response pattern over STIO or SSEO or SS works beautifully for single-agent workflows but degrades under high concurrency multi-agent fan-out scenarios. These are not bugs, they are the logical consequences of MCP's deliberate design scope. The question now is whether that scope is a fatal flaw or a feature. And that verdict requires a structured framework, which is exactly what we built in Chapter 2. There is a recurring argument on Hacker News and in AI engineering circles that MCP is a fad, that it will be obsoleted the moment multi-agent frameworks mature. Let's apply the 3 survival laws we established in Chapter 2 and deliver a structured verdict. Law 1. Does the protocol solve a real, recurring integration pain? Yes, unambiguously. The LLM-to-tool integration problem was being solved with 1,000 incompatible bespoke adapters. MCP provides the USB standard that was missing. Law 2. Is the scope narrow enough to be implementable but wide enough to be useful? This is where MCP's design shines. It does exactly one thing, connects LLMs to tools, and it does it with a 4-primitive surface area that any developer can internalize in an afternoon. Compare this to SOAP, which tried to be an enterprise integration bus and collapsed under its own ambition. REST survived because it embraced HTTP's existing semantics and stayed narrow. MCP is making the same bet. Law 3. Does the ecosystem create switching costs before alternatives crystallize? The hundreds of community MCP servers already deployed represent real switching costs. Ripping out MCP means rebuilding every one of those integrations. My verdict as an information systems architect: MCP is not a fad. It is the rest of AI tool integration, a protocol that will persist precisely because it refused to be more than it needed to be. The real question is what sits above it, and that is exactly what A2A answers. In the next chapter, we dissect Google's vision for agent-to-agent coordination, and you will see immediately why MCP and A2A are not competitors. They are complementary layers of the same emerging stack. In the previous chapter, we saw how MCP treats the world as a hub-and-spoke model. One orchestrator, many tools, all under human control. But what happens when the agents themselves need to negotiate? That is the design problem Google set out to solve with agent-to-agent, A2A. The foundational innovation of A2A is the agent card, a machine-readable JSON manifest published at a well-known endpoint, typically at the path.wellknown/agent.json. Think of it as a business card that an agent hands to any peer that wants to collaborate. The agent card declares the agent's name, its supported capabilities, the input and output modalities it accepts, text files, structured data, and critically, the authentication schemes required to interact with it. This is not a registry lookup. This is a peer discovery model. Any agent that can reach the endpoint can read the card and decide, autonomously, whether this peer is capable of handling a delegated task. Compare this philosophy to MCP, where the orchestrator already knows what tools exist because a human configured the server list. A2A assumes no such pre-configuration. Find each other at runtime, like microservices registering with the service. If you have worked with Kubernetes Service Discovery or Console, this pattern will feel immediately familiar. But here is the critical question. If agents are discovering each other autonomously, who is governing what they are allowed to discover? Once an agent has read a peer's agent card and decided to delegate work, it creates what A2A calls a task object. And this is where A2A makes its most important architectural statement. The task is a first, persistent entity with a formal life cycle. In distributed systems theory, this is the difference between RPC semantics and workflow semantics. MCP follows RPC semantics. You call a tool, you wait, you get a result. A2A follows workflow semantics. You submit a task, it transitions through states, and you can inspect or resume it at any point. The task state machine has 5 formal states. First, submitted, the task has been received and queued. Second, working, the remote agent is actively processing. Third, input required, the agent needs additional information from the caller before it can continue, enabling a human-in-the-loop or agent-in-the-loop pause. Completed, the task finished successfully with a result artifact. Fifth, failed, the task encountered an unrecoverable error with a structured error payload. This state machine maps directly to the patterns you would recognize from BPMN workflow modeling or SOAP patterns in microservice architectures. The input required state is particularly significant. It means A2A natively supports multi-turn, interactive agent workflows without hacking the protocol. A long-running financial reconciliation task, a multi-step code review, a document negotiation workflow, all of these can be modeled cleanly inside a single A2A life cycle. Now, how does the caller receive these state transitions in real time? The answer reveals another fundamental design choice, and it is one that separates A2A from nearly every tool calling protocol that came before it. The A2A protocol delivers task state transitions and progress updates through server-sent events, SSE, a unidirectional streaming protocol built on top of HTTP. When a caller submits a task, the remote agent keeps the HTTP connection open and pushes event stream messages whenever the task state changes. Partial results become available, or intermediate artifacts are produced. For scenarios where a persistent connection is impractical, think mobile clients or serverless functions with short lifetimes. A2A also supports push notification callbacks via webhook URLs declared at task submission time. This async-first design is a deliberate architectural choice. Consider the contrast with MCP. MCP's tool execution model is fundamentally synchronous. The orchestrator sends a request and blocks for a response. That works perfectly for calling a database query or invoking a search API, where latency is measured in milliseconds. But agent-to-agent delegation is fundamentally different. A remote agent might need to browse the web, write and execute code, call multiple downstream services, and synthesize results over a period of seconds or even minutes. Blocking a synchronous connection for that duration is architecturally indefensible. SSE solves this elegantly. It uses plain HTTP, passes through corporate firewalls and API gateways without special configuration, and delivers ordered, reliable event streams without the bidirectional complexity of WebSockets. In OSI layer terms, MCP optimizes for session layer efficiency in short transactions, while A2A optimizes for application layer reliability in long-running distributed workflows. Both are correct for their respective target problems, and that distinction is precisely what we will weaponize in the head-to-head comparison coming next. Security architecture reveals what a protocol's designers truly believe about its deployment environment. MCP's security model is grounded in trust. The orchestrator trusts the MCP server because a human explicitly configured that connection. It is a walled garden assumption. A2A's security model starts from the opposite premise: assume the peer agent is untrusted until it proves otherwise. This is zero trust applied to agent communication, and it aligns directly with NIST SP 800 to 200 trust architecture principles. A2A delegates authentication entirely to open API authentication schemes, the same specifications that govern enterprise API security today. This means OAuth 2.0 authorization code flows, client credentials flows for machine-to-machine scenarios, API key schemes, and HTTP bearer tokens are all first-class authentication mechanisms in A2A. The agent card itself declares which schemes are required, so a peer agent knows before attempting a connection what credentials it must present. This design choice has a profound architectural implication. A2A agents can be deployed behind the same API gateway infrastructure that already secures your enterprise APIs, Kong, APG, AWS API Gateway. No new security perimeter is required. Furthermore, because the security model is declarative and carried in the agent card, it supports capability-based access control. An agent card might declare that certain skills require elevated OAuth scopes, while others are publicly accessible. For enterprise architects who have spent years building zero-trust network architecture, A2A's security model will feel immediately legible. But here is the uncomfortable question. If every agent interaction requires OAuth negotiation, what happens to your system's latency profile at scale? That trade-off is real, and the ecosystem data tells a sobering story. A protocol's theoretical elegance means nothing if its ecosystem cannot support production workloads. So let us apply the survival law of ecosystem gravity. A standard lives or dies by the number of working implementations, not the quality of its specification. Where does A2A stand today? Google Vertex AI Agent Builder has native A2A support. That is the anchor implementation, and it is production-ready in Google Cloud environments. Enterprise partners announced at Google Cloud Next 2024 include Salesforce, SAP, ServiceNow, and Workday, representing a significant surface area of enterprise workflow automation. On paper, this looks like critical mass. But the gap between announcement and production-ready implementation is significant. As of mid-2025, most partner integrations are at the SDK preview or beta stage. The number of open-source A2A server implementations is an order of magnitude smaller than the MCP server ecosystem, which already has thousands of community-built connectors. Developer mindshare measured by GitHub stars, Stack Overflow questions, and community forum activity heavily favors MCP. This mirrors a pattern we have seen repeatedly in protocol standardization history. AP had IBM and Microsoft behind it. WSDL was technically rigorous, yet REST won because it was simpler and developers could build implementations in an afternoon. A2A's specification complexity, the agent card schema, the task state machine, the SSE streaming requirements, the OAuth integration, creates real adoption friction for individual developers building prototype systems. For enterprise platform teams with dedicated infrastructure engineers, that friction is acceptable. For the long tail of developers who will ultimately determine ecosystem gravity, it is a meaningful barrier. The implication for your architecture decision is coming. But first, we need to confront A2A's structural risks directly. Every protocol has structural risks, and honest architectural analysis requires naming them without flinching. A2A has 3 risks that any senior engineer should weigh before committing to it as a foundational standard. Specification complexity as an adoption barrier. The A2A specification covers agent cards, task state machines, SSE streaming, webhook callbacks, OpenAPI auth integration, and multi-turn interaction flows, all in version 1. Compare this to HTTP's core specification or AMQP's message model. The cognitive overhead of implementing a compliant A2A server from scratch is substantially higher than implementing an MCP server. In the SOA era, this exact problem killed WS specifications. They were technically superior to REST in several dimensions, but their complexity drove developers towards simpler alternatives. Second, and more structurally dangerous, is Google's single-vendor governance. As of today, A2A has no neutral standardization body shepherding its evolution. The specification lives in a Google-controlled GitHub repository. Google makes the architectural decisions. Compare this to how HTTP, WebSockets, and OAuth 2.0 are governed by IETF working groups with multi-vendor participation and public comment processes. Without a body analogous to DO3C or IETF, enterprises face a strategic risk. What happens to your A2-based infrastructure if Google deprecates or significantly pivots the specification? We have seen this before. Google Reader, Google Cloud IoT Core, Google Stadia. Third, the absence of a neutral certification or compliance testing framework that two A2A implementations may exhibit subtle interoperability gaps that only surface under production load. These are not reasons to dismiss A2A. They are the exact risk factors you must mitigate in your architecture. And now that we have fully dissected both protocols, the head-to-head analysis will give you the decision framework to choose, combine, or hedge between them with confidence. Now we place both protocols side by side, and the difference is immediate. MCP is a vertical interface, an AI agent reaching downward to grip a tool, a database, an API. Communication flows in one direction, agent commands, tool executes. A2A, by contrast, is horizontal, peer agents negotiating tasks, delegating work, reporting status. Think of it through the OSI model lens. MCP operates at the application-to-service boundary, analogous to a session layer handshake between a client and a resource. A2A operates at the internode coordination layer, analogous to how routing protocols negotiate between autonomous systems. Conflating these two is exactly the mistake that causes agent stacks to break at scale. You would not use BGP to configure a network interface. and you would not use MCP to coordinate two competing orchestrator agents. The design intent is not just different, it is architecturally orthogonal. But here is the uncomfortable question every architect must answer. If these protocols are so clearly separated, why do most production teams still try to force MCP into coordination roles it was never designed to handle? Security is where the architectural mismatch becomes a real operational liability. Let us be precise. MCP's trust model was designed for a local or semi-trusted environment. The assumption is that the agent and the tool server are within the same trust boundary, the same process, the same container, or at worst the same internal network. Authentication is lightweight, often Auth 2.0 or API key, and authorization is coarse-grained. You either have access to a tool or you do not. The threat model does not account for a malicious agent impersonating a legitimate one. Now consider A2A. Google designed it for enterprise multi-tenant environments where agents from different organizations, different vendors, and different trust zones must coordinate. Authentication is mutual TLS or JWT with signed agent identity cards. Authorization is fine-grained, scoped to specific task types, data classifications, and time windows. The threat model explicitly includes agent impersonation, task injection, and replay attacks. Here is the critical engineering insight from the SOA and ESB era. When you try to use a lightweight internal protocol, like early SOAP implementations, across organizational boundaries, you do not get security. You get the illusion of security. MCP in a multi-agent cross-boundary deployment is precisely that trap. But does A2A as security model introduce enough overhead to make it impractical for rapid prototyping? Maturity matters enormously when you are making an architectural commitment that will be expensive to reverse. Let us score both protocols honestly across 6 dimensions that any seasoned enterprise architect or 정보관리기술사 XM candidate should evaluate before standardizing on a protocol. MCP launched in late 2024. It has a stable specification, a rapidly growing ecosystem of tool integrations, strong Anthropic-backed documentation, and a community that has already produced hundreds of open-source MCP servers. Production deployments exist at meaningful scale. However, its governance is still effectively controlled by a single vendor, and its specification evolution process lacks the formal RFC structure that enterprise procurement teams demand. A2A is newer, announced in April 2025, with a specification that is still maturing. Tooling is nascent. Production deployments are limited to early adopters. But its governance model is explicitly multi-stakeholder. Its specification process is more rigorous, its long-term trajectory, particularly for enterprise compliance frameworks like ISO 27001 or NIST ARMF, is significantly stronger. This mirrors the WS security versus lightweight REST API security debate of the 2000s. The heavyweight, governance-rich standard won in regulated industries. The lightweight standard won everywhere else. The question for your architecture: which industry are you building for? That answer will determine everything about the choices we discuss in the next section. Here is the insight that resolves the entire MCP versus A2A debate. They are not competitors. They are layers. The mistake most teams make is treating this as a binary choice. Pick one protocol and build everything on it. That is the same error the ESB vendors in the early 2000s when they tried to make a single integration bus handle both internal service orchestration and external partner coordination. It collapsed under its own weight. The correct architecture is layered. At the top, you have the inter-agent coordination layer, where A2A governs how your orchestrator agent delegates tasks to specialist agents, how those agents report status, how they negotiate task boundaries, and how failures propagate upward. Below that, at the capability access layer, each individual agent uses MCP to call its tools, its database connectors, its API integrations, its code execution environments. These two layers operate independently. An A2A task delegation event does not care which MCP tools the receiving agent will use to fulfill it. An MCP tool call does not need to know that it was triggered by an A2A task rather than a direct user request. This separation of concerns is the foundational principle that makes multi-agent systems maintainable at enterprise scale. But a layered diagram only takes you so far. The real proof is in a concrete workflow. So let us walk through exactly that. Let us make this concrete with an enterprise document processing pipeline, the kind of workflow that financial institutions and legal firms are deploying right now. A compliance document arrives. The orchestrator agent receives it via an A2A task initiation message, which includes the task type, required output format, and security classification. The orchestrator uses A2A to delegate 2 subtasks, one to a document extraction specialist agent, one to a regulatory compliance checker agent. Notice, these are A2A task deletion calls, not MCP calls. Each specialist agent is a peer, not a tool. Now inside the document extraction agent, the agent uses MCP to call 3 tools: a PDF parser server, an entity recognition API server, and a document storage write server. These are MCP calls, structured, synchronous, tool access operations within a single agent's capability boundary. The compliance checker similarly uses MCP to call a regulatory database lookup server and a rules engine server. When both specialists complete, they respond to the orchestrator via A2A task completion messages with structured results. The orchestrator aggregates and delivers the final output. The boundary is explicit. Every cross-agent communication is A2A. Every cross-tool communication is MCP. Break that rule once, and you have the architectural debt that will consume your next 6 months of debugging. The next section will give you the decision framework to avoid that debt from the start. Every architectural decision needs a decision framework, not just a narrative. Here are the 4 questions that determine your protocol architecture. The same questions a 정보관리 기술사 reviewer would ask when evaluating your system design submission. First, how many autonomous agents does your system have? If the answer is 1, you need MCP only. A single agent connecting to tools has no need for A2A overhead. Second, do your agents coordinate, compete, or negotiate? If they share tasks or delegate work to each other, you need A2A at the coordination layer. MCP alone produce brittle point-to-point agent communication that does not scale. Third, what is your trust model? If all agents are within your organizational boundary and share a deployment environment, MCP-level security may be acceptable. If any agent is external, a vendor agent, a partner system, or a separately governed service, you need A2A's identity model. Fourth, are you building for enterprise compliance? If your deployment must satisfy ISO 82701, SC2, or NIST AIR-RMF audits, A2A's governance structure and fine-grained authorization will matter at procurement time, often more than technical performance benchmarks. The answer in most production enterprise systems, you need both. But now you know exactly which layer each belongs to, which trust model each assumes, and which maturity level each has reached. That knowledge is what separates architects who build durable systems from engineers who rebuild them every 18 months. In the final chapter, we will look at where these protocols are 2025 and beyond, and which architectural bets are worth placing right now. Let's apply everything we've built to a concrete forecast. History doesn't repeat, but it rhymes. And the rhyme pattern here, unmistakable. HTTP started as a CERN internal draft in 991. It took 6 years to reach RFC 2068, and another 3 before enterprises stopped debating whether to adopt it. OAuth followed a nearly identical arc, born at Twitter, incubated at Google, then handed to the IETF in 2010. Today, MCP is at the same inflection point HTTP occupied in 1994. It works. It spreads. But is not yet a standard. It is a de facto convention. A2A, by contrast, launched with explicit multi-vendor backing and a governance model that signals intent to submit to a neutral body, exactly as OAuth 2.0 was designed from day one to be IETF ready. Our 3-year forecast. By 2026, MCP reaches critical mass as the dominant tool interface convention, equivalent to HTTP 1.0 adoption. By 2027, it achieves its first formal standardization submission, the IETF or D33C being the most structurally probable targets. The question is not which protocol survives, both will. The question is which layer each will own, and that answer is already written in their architecture. But here is most architects are getting wrong about that timeline, and we will expose it in the next scene. 3 structural futures are possible, and they are not equally probable. First, convergence, a unified protocol that absorbs both MCP's tool semantics and A2A's agent negotiation primitives. This sounds elegant, but history is brutal here. SOAP tried to unify RPC and messaging. It collapsed under its own weight. The probability of true convergence is low, roughly 15%, because the 2 protocols solve fundamentally different coordination problems at different OSI equivalent layers. Merging them would produce something that does neither well. Second, permanent coexistence at distinct layers. This is the HTTP plus WebSocket model. HTTP handles request response. WebSocket handles persistent bidirectional streams. Neither replace the other because they occupy non-overlapping problem spaces. MCP and A2A fit this pattern almost perfectly. MCP at the tool interface layer, A2 at the agent negotiation layer. Structural probability, 65%. This is the dominant scenario. Third, winner takes all displacement. One protocol extends its scope to absorb the other's use case. This happened when JSON RPPC displaced XML RPC, and when REST displaced SOAP and Web APIs. The risk here is real. If Anthropic extends MCP with agent-to-agent primitives, or if Google's A2A gains tool calling extensions, one could crowd out the other. Probability, 20%. Now here is the critical insight for your architecture decisions. The coexistence scenario is not passive. It requires you to build for it deliberately. Failing to do so is exactly the trap this lecture was named after, and the prescription comes next. So how do you build a system today that does not become a rewrite candidate in 18 months? The answer is an abstraction layer, and this is not a new idea. It is exactly what JPA did for SQL dialects in the early thousands. You did not write Oracle-specific SQL directly into your application logic. You wrote to the JPA interface, and the dialect adapter handled Oracle, PostgreSQL, and MySQL underneath. Your application logic never changed when you switched databases. Apply this pattern to agent coordination. Define a protocol-agnostic agent coordination interface, let's call it the ACI layer, that sits above both MCP and A2A. Your orchestrator talks to the ACI. The ACI delegates to an MCP adapter for tool calls and an A2A adapter for agent delegation. When the protocol landscape shifts, and it will, use the adapter, not the architecture. The ACI layer exposes 4 canonical operations: tool invoke, agent delegate, capability query, and task status. These 4 primitives are sufficient to express any coordination pattern that either MCP or A2A currently supports. The key architectural constraint is that no business logic or orchestration logic should contain a direct reference to MCP message schemas or A2A envelope formats. That coupling is the trap. The moment you hardcode to a protocol's wire format, you have bet your architecture on that protocol's survival. Build the abstraction now, while the cost is low, before your production dependency graph locks you in. But knowing when to finally commit to a protocol is equally critical. And the specific signals that tell you it is safe to do so are precisely what we examine next. Maintaining an abstraction layer indefinitely has a cost. At some point, you need to commit to optimize for one protocol, negotiate vendor contracts, and train your team deeply. But committing too early is the trap. So what signals tell you the window is open? There are 4 concrete categories to monitor. First, GitHub commit velocity. When a protocol's core repository sustains more than 50 commits per week, from more than 10 distinct organizational contributors for 3 consecutive months, it has escaped single vendor dependency. That is a green signal. Second, enterprise production announcements. When 3 or more Fortune 500 organizations publicly declare a protocol as part of their production AI infrastructure, not a pilot, not of concept, the network effect has crossed the tipping point. Third, standards body submission. An IETF Internet Draft or DOE3 working group filed for the protocol means governance has been formalized. This is the single highest confidence signal available. Fourth, tooling ecosystem depth. When major API gateways, Kong AWS API Gateway, Azure ASIPA, publish native protocol adapters, the operational risk of commitment drops sharply. Monitor these 4 signals on a quarterly review cadence, until at least 3 of the 4 are green for a given protocol. Maintain the ACI abstraction. The cost of the abstraction layer is always lower than the cost of a forced migration. And with that strategic positioning established, we are ready to close with a full knowledge map that ties every concept in this lecture together. Let's close with a full knowledge map. We opened this lecture with a failure state. Agent stacks breaking not because the code was wrong, but because the protocol assumptions were wrong. From there, we built 6 chapters of structured analysis. MCP is the tool interface protocol, the vertical bridge between an AI model and external capability. A2A is the agent coordination protocol, the horizontal bridge between autonomous agents negotiating tasks. Mapped to the OSI analogy, MCP operates at the session of presentation. A2A operates at the session layer for peer-agent communication. They are not competitors, they are complements. And the architecture that treats them as competitors will fail. We applied the SOA-ESB MSA historical lens and derived 3 survival laws. Specificity of scope protects survival, multi-vendor governance, acceleration, and abstraction depth determines longevity. We ran the head-to-head comparison across 6 dimensions: discovery, execution model, security, statefulness, interoperability, and operational complexity, and we closed with the strategic forecast: 65% probability of stable coexistence. The ACI abstraction pattern as your defensive posture, and 4 concrete signals that tell you when it is safe to commit. The adjacent topics that will deepen this knowledge are LLM ops, specifically how protocol telemetry integrates with model observability pipelines, agent memory systems, which determine what state persists across A2A task handoffs, and enterprise AI governance frameworks, where protocol selection becomes a compliance and auditability decision. The multi-agent era is not coming. It is already here. The architects who understand the protocol stack will build the systems that last. Those who do not will be debugging the trap this lecture was named after.